problem. So we're basically going to look at a drop bouncing on a soap film. Okay. And so we saw the talk you saw motivated this. So you have these drops bouncing on a fluid bath, on a vibrating fluid bath, and they exhibit all sorts of features of quantum mechanics. And so now we actually have a model for their dynamics, but this is the first step in that direction. So the difficulty in the model is the inertia of the fluid is actually important. So things get rather complicated. But to leading order, we'll see that you can think of a drop hitting a free surface like a linear spring. Okay, so I hope to convince you of that today. And so, we'll see this through looking at a drop bouncing on a soap film. So first we look at a drop hitting a stationary film and get criterion for breakthrough, and then we look at a drop bouncing on a vibrating film. And on the vibrating film, we'll see that you can get steady bouncing states, and then you get period doubling transitions and the onset of chaos in the bouncing. And so this is really a classic chaotic oscillator, and so all of this sort of mathematics, when used for develops in dynamical systems, can be applied to this system. And I think it's one of the simplest fluid mechanical chaotic oscillators looked at. And so so the two problems. The first is, what's the criterion for breakthrough if we have a drop hitting a soap film? So it's the same fluid in the drop and in the film. And we expect the key parameter here, we don't expect viscosity to be dominant. We expect it to be the Weber number, which is basically the kinetic energy of the drop to the surface energy. Okay. And then in the second experiment, we look at a drop bouncing on a film. We do a little trick to stabilize the drop on axis, because soap films don't care about gravity because they're too light. So they're basically going to be flat no matter what. And so unless your system is perfectly level, you'll get a film like this, and the drop will just bounce off. So the way you get around this is we apply a little bit of suction here. So by applying suction, we make this slightly concave, and so the thing bounces on axis. So we're just interested in stationary bouncing. Okay? And so here we drive the system now with a loudspeaker, and so that it has this characteristic acceleration. So that's the frequency, and that's the amplitude of the driving. Okay? And so the fluid we use is glycerin water. So it's twice as viscous as water. Surface tension around 22 times per centimeter. Drop radius around 1 millimeter, and the frame radius around 8. So we use different frame sizes for these two experiments. But in any case, a Dove. Dove is a soap. Right. Yeah. So it's just a commercial soap. Yeah. Okay. So right. So what can happen? So we see the thing impacting. On the left it bounces. On the right it goes through. Right. And so all there had been before this was some scaling arguments, which my old supervisor done, Howard Stone, but we, I think, solved this pretty convincingly. And so in addition to, so basically when the thing goes slowly, it will bounce. If it goes quickly, it will break through, right? And there's actually a whole family of possibilities. So the thing to note is that when it passes through, it actually doesn't break the film, right? Which is interesting. Kind of think, oh, it's going to break when it breaks it. But actually what happens is it goes into the film, so it hits, then the air layer between the drop and the bath gets sufficiently thin that it merges, so then the drop is inside the film, and then it falls out of the bottom, right? But it doesn't break the film. Because again, the film it's a soap film, so it doesn't want to break. Right? It has, it's basically elastic by virtue of the surfactants. And so here, so it enters the film, and parts of it can be thrown up or down. So when it can be ejected up or down. I think the one at the bottom, things are ejected both up and down. Is that right? There's one of them. I can't remember which one. But yeah, sometimes you'll get things going both up and down. Wait. This one. This one. You see that? So you can see a small drop being shot up. So most of it goes down, but part of it goes up, right? So you can, yeah. Okay, and so if we look at the probability of passing, its dependence on the Weber number, there's basically a critical Weber number around, say, 15, beyond which the thing will pass through. So if you hit a Weber number less than 15, the thing will not merge and it will simply bounce. Okay, and so this is one simple question we'd like to be able to rationalize. Why 15? Okay, and so the model is quite simple. And you guys are all capable of doing this. We say basically, so in the impact, we have this air layer between the drop and the film, and this communicates stress between the two, right? So it's a lubrication layer. So because it's so thin, there can be no gradients in pressure across the thin layer. So basically, its role is simply to communicate stresses from here to here, from here to here, right? So we know that the force acting on the film is equal and opposite to the force acting on the drop, okay? So what you do is, hydrodynamically, you solve for the pressure within the film, and that's a normal stress acting here and here. So what's that saying is that if we, by tracking the shape of the film, we're also getting the force here on the drop. Okay, and so if we assume that the drop doesn't change much in its shape, which it doesn't, certainly at lower speed impacts, then the only surface energy that's changing is out of the film. Okay, and so we can, and so if we know the shape of the film as a function of position, then we know the energetic cost to its moving a certain amount, a distance dx downwards, and that gives us the force. So the gradient of the surface energy with respect to x is the force acting on the drop, right? And so the approximation is that this thing is quasi-static. That is to say, the shape of the film at any given instant only depends on the current position of the drop. Okay, and so that turns out to be true, and it's true because basically the wave speed on soap films is very high. It's about 3 meters per second, and so if our motion is much smaller than that, these waves basically go off immediately and communicate information to the walls and back. And so you basically just have this thing responds quasi-statically. So basically, again, you tell me the position of the drop, and then you calculate the interface by finding the minimal surface. Right? It's a soap film. So we know this has. So basically, you say there's a spherical cap which masses onto the drop, right? And then you have a minimal surface here, so it has to have zero mean curvature, and the only surface that has zero mean curvature in 3D is a catenoid. Right? So we basically match a spherical cap onto a catenoid. That gives us the shape of the film as a function of the position of the drop. So that gives us then the force field acting on the drop. Okay. Okay, and so it turns out when you plot this, it looks like this. So this is the force acting on the drop as a function of intrusion depth of the drop. And so for small intrusion depths, in particular in this bouncing regime, this is all we have to worry about, and it's basically a linear dependence, which is very nice, right? So we can suddenly say, oh, well, the interface, the soap film is like a linear spring. Okay? So it's a linear spring, and the spring constant, so F equals kz, and the spring constant is just linearly proportional to the surface tension. It turns out, so this coefficient actually depends on how big the ring is relative to the drop size, but you can calculate it as a function of the ring size. Okay? So it's a very nice feature, and you can hope, because of this result, this sort of good fortune in this being linear, we can actually write down equations of motion and hope to get a good description of the system. Right? Okay, so our breakthrough criterion, first of all, So again, this this is the result is going to depend on this beta parameter, which is the film radius to the drop radius. But basically, your criterion for breakthrough is that the initial drop kinetic energy is greater than the surface energy at breakthrough. So at breakthrough, the interface basically comes down like this. So it's a catenoid, and then it goes vertical. Right? And if you go beyond that, it breaks through. So you can then write this. So you can calculate that surface energy at this point, if you know the size of the drop and the size of the rail. And you can then look to see what the critical Weber number is, okay, for a given beta, which is this geometric factor. So again, this radius to this radius. And this gives us the predictions for the critical breakthrough Weber number. And so if we look for our experiments were done with beta equals 10, which predicts a breakthrough, a critical Weber number of around 15, right? Which is exactly what we had. So that gives us some confidence in this linear spring model of the soap film, okay? And so other thing which gives us confidence in this model is the fact that the contact time scales as square root of m over k, right? Because that's the time scale for a linear spring. If you have a mass m on a linear spring with spring constant k, then the spring time is square root of m over k. Okay, so that we can see that. So what this shows is that this contact time. So I mean, what is the contact time for a drop bouncing on a film? It's basically, of course, it never actually touches, but it's basically the time during which the film is being deformed by the drop, right? Okay, so you basically measure this, and you see that it doesn't depend on the incoming speed, which is sort of surprising. Right? It comes out to be this square root of m over k. So there's a weak dependence which we can rationalize later, but to leading order, we see that this film is behaving like a linear spring. And certainly in terms of the criteria for crossing the film and in terms of the contact time. Okay, so the only other thing we need to do, so we want to write down an equation of motion for this drop, right, for the bouncing drop, and we're going to drive it. But we need to get some idea of the dissipation in the system, because in order to really write down the equation of motion, we have to get the dissipation. So we can define a coefficient of restitution. So this is the outgoing speed relative to the incoming speed, and we know this is always going to be less than 1. So we can define it as here, and we can plot so the change in Weber number over the Weber number. And here we see that this does change on change with impact speed. In particular, the higher the incident speed, so again, this is our Weber number, the higher the incident speed, the more energy is lost. Okay? And you can rationalize this scaling if you consider that the work done by the film during impact, it's going to be rho u squared, that's the characteristic pressure. Then you have a speed times a time, which gives you a length. So it's basically a force over a given length. So this is the work done, and so that's where the 3 halves comes from. Okay, okay, so this is just empirical, right? We're just measuring this, and so we're going to throw in a term in our equation which is consistent with this, right? And you can argue that we should have another type. It should look like this. It should look like this, but we don't care because it works, as we'll see. And we've actually tried different types, but we've chosen this form. So this is the equation of motion of the drop now. So mass times acceleration of the drop. No one's going to argue with that. No one's going to argue with this. Then we have our linear spring force term, and that acts, this Heaviside function says it only acts when the drop is in contact with the film, right? So that's going to act over the contact time. Then we have this dissipation term, and we're modeling it so that it too happens while the drop is in contact with the film. So in reality, it has to do with the dissipation of the generated by the drop oscillation. So that's actually, if you do the scaling, it turns out that that's the biggest source of energy loss. But in any case, we model it this way just for the sake of expedience in terms of the analysis. And we've tried this Z z prime squared form is, we have to choose that to be consistent with the data on the observations of the dissipation. But we basically, we pull this off the data as well, right? So this we pull off the data. Again, this form is suggested by this scaling, which we've observed, and the coefficient is from the experiments. So, and we've calculated this. Okay, so it's kind of nice. You have a nice ODE, and this is what it predicts for. So this is a drop just hitting a film. So it decreases in amplitude. This is actually precisely from this sequence, and you can see why the thing basically bounces out of the field of view. But this is what the model predicts, and this is what the experiments give. So we can only see the drop when this is the blackout zone where it's behind the frame. But it's, so it's actually, and again, so the fact that it's jumping to success, the peaks of its jumps get progressively smaller. It's because there's energy being lost to dissipation, which is being modeled by this term here. Right? So it's actually, it does a nice job, right? So one can't help ask for much better agreement between theory and experiment. Of course, we've sort of chosen our dissipation term to ensure that. Nevertheless, so let's see what we can do with this now. Because now you can ask the question, now we basically have the equation of motion for this thing. Now we can drive it, right? So now we have a force dissipative system, and we can look for chaos, okay? So, we now take our frame, we drive it up and down with an amplitude B and frequency F, and let's see if we can model these bouncing drops. Okay, so what do you see, crudely speaking? You say, okay, let's look at the frequency and the bouncing behavior. So let's look at the bouncing behavior as a function of the frequency of the film and the driving amplitude. So this is, again, the forcing acceleration divided by g. So this, we see, first of all, that you don't get any action above the natural frequency of the film, which is around 55 hertz. So if you, should be intuitively familiar. If any of you have stood on a trampoline, you know, you go like that. If you go like this, you don't move, right? So you basically, there's a critical frequency below which you can expect to jump. And the same is true on the soap film. So if we're below this natural frequency, then there's a critical amplitude of vibration above which the thing will bounce. If you're driving it if the amplitude is too low, then the drop will coalesce with the film. So it'll sit on the film, and then just the air layer will drain, and it will merge with the film. But above a critical threshold value, you will get bouncing states. Okay. Okay, so you get, and it's very rich. So you get various different bouncing states, which we'll call MN. So I guarantee you won't remember this, because I don't remember it. So bouncing state, Mn bounces n times in m forcing periods. So the 1-1 state, the period of the bouncing is the same as the period of the forcing. Here the period of the bouncing is twice the period of the forcing, and here it's 3 times. So I want you to note one thing. These 3 are all solutions observed with this exactly same forcing parameters. So the same acceleration, the same amplitude, the same drop. So they ask the question, how is it that I can have 3 different periodic solutions with the same forcing? Okay, and then we see this guy here. So here we call this a 3-3 mode. So it has 3 different bounces with 3 different amplitudes. And this cycle of 3 jumps is completed after 3 periods of the forcing. So the bouncing, it takes 3 periods. Its periodicity is based on 3 forcing periods, right? Okay? How clear was that? Okay, but you see what I mean, right? So we'll come back to this mode later, but it is perfectly periodic, but it's yeah.
How do you experimentally select one of those 3 modes?
So I'll tell you right now, it depends on the phase, right? So which of these solutions you get, because there's a variable which is phase, right? So it's going to get a different kick depending on when it hits the film. If it hits the film when the film's coming down, it's going to get a little kick. If it hits the film when the film is coming up, such as here, then it gets a big kick. Okay? So there can be different periodic solutions depending on phase of impact for the same forcing. Okay? Okay, so, but the nice thing is we have the equation of motion, right? Off we go. So we can describe this system exactly. Right? So we have exactly what we had before, and then we have the forcing. So we're basically saying, we're in an accelerating frame now. So this is like our D'Alembert force. So this is our wait, that shouldn't be the G. Oh yes, it should. Yeah, gamma is the forcing acceleration over G. So, but this is basically simply from the fact that we're going to describe this now in the accelerating frame of the frame. Unfortunate dual use of the word frame in English. But okay, so again, same equation of motion, but now we have a forcing term. So it's just like you're turning gravity on and off, right? Okay, so we have. So this is again what we observe. So these are just those four states these are the three states I showed you before. These guys here. So the 1, 1, 2, 1, 3, 1. And so what we do is so what is this data? We take a slice through the center line of the drop, okay, at each frame, and then we step it forward in time. So you're going to see. So it looks like the data looks like. Basically gives you the trajectory of the drop. So the 1, 1 mode is just the things just going up and down like this, and then the 2, 1 things, the things are. So this is time, and this is position. Yeah. Okay, and so you see, again, these are the same forcing, so the same forcing acceleration and frequency. The Weber number is different. Weber number is based on the impact speed. So. Here you can see it's landing at a relatively low speed, here a high speed, and it's getting a bigger kick because the phase is different between these three experiments. And then, and this is interesting because at this forcing frequency, whatever you hit it with, right, is however you initialize the drop, there will be some transient. So that's to say, whatever phase and speed you drop it at, it will lock onto one of these three solutions. Okay? Those are the only possible solutions. So why 3? Why not 5? Why not 10? Why not 1? And so, but we'll be able to answer that, okay? Because we have a complete mathematical description. And so, of course, the only limit is that if you hit it, if you drop the drop from too high, it will break the film. But provided you don't break the film, there will be some transient, such as you see here, then it locks onto one of the three solutions. Okay? Okay, so here are so we have the possibility of three different solutions by virtue of the different impact phases. Okay, and so these are the numerical solutions based on the model. So this is the trajectory versus, so basically the height as a function of time, and you can compare the landing and the takeoff and landing times with experiments, and they match pretty well. Okay. So, and again, it's the difference in phase which allows you to rationalize this sort of what's the word? Multiplicity. The fact that you can have more than one solution. Okay, so and now we can look at the use this sort of dynamical systems language. And so if we plot now speed against position, we have a limit cycle. So this is for these periodic solutions. So this, by the way, is the kick it gets during the impact. So if you look at the power spectrum, it's sparse, and you have a negative Lyapunov exponent. So what that says is if you start somewhere off this curve, you'll soon fall onto it. So the Lyapunov exponent gives an indication of how quickly you converge to a limit cycle or diverge. And if it's chaotic, you're going to get a positive Lyapunov exponent. Okay, and so we can describe the system in terms of a 2D iterative map. So we have, we can use a Poincare section, and we're interested in the speed of impact and the phase of impact. Okay? So we can solve numerically, so we can just integrate our equations motion and get this map. And we can calculate from this map how much energy is being gained by the during impact, and this is going to depend on the speed of impact as well as the phase of impact. Okay? So again, so we have basically, this is the position, so we're going to characterize in terms of its properties at impact, so at y equals 0. So we have the speed and the phase of impact, these two guys. Okay, and so this is basically saying how much energy it's gaining during impact, so per cycle, as a function of the speed of impact and phase of impact. Okay, and so there are zeros. So in the shaded region, it's getting extra energy, so it's leaving with more energy than it came in with, right? And if it's landing in the white region, then it's losing energy. It's coming in with more energy than it's going out with. Okay, and so we know that if it's going to be perfectly periodic, it has to land on the zeros, right? So these are theoretical predictions for the for these three different solutions: the 1-1, 2-1, and 3-1 modes, right? And we see that, and these are actually the experiments. So we see we're very close in terms of rationalizing them. So, but this is saying, so this is a Poincare section, but the thing's just coming down, like this solution is just going boom, 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 right? But we know for these more complex orbits, like the 3-3 mode, this is a 3-3 mode here. So these are different forcing accelerations, these four plots. We know that it can have an orbit in which the total energy gained in all three bounces is 0, right? So you can bounce across this zero line, and so that happens. Where's these ones down here? So it can have two. It can bounce like this, and as long as the total energy in both bounces is 0, then you can have these more complex states, right? It's here. So the 3-3 one, which we saw, which is the bouncing with three different amplitudes, is this one. So it's basically on two of the bounces it's getting a kick, on the other one it's losing energy, right? But you have this possibility of more complex orbits, and we'll see that you can get chaotic. If you have chaotic maps, then they basically just go everywhere. But you can rationalize in this way the fact that you can get 1-1, 2-1, 3-1. You can't get the 4-1. Basically, you can't get if you with this amount of energy kicked in, you can't support a 4-1 case. It's just beyond the zero line. Okay, and so and then we have complex, so more complex periodic and aperiodic mode. So this is our 3-3 mode. So again, it's periodic after 3 bounces. And then we have a period doubling transition from a 1-1 to a 2-2. And then we have a chaotic solution, which is just a mess, which follows. So basically, as you increase the forcing, you go from periodic to period through a series of period doubling transitions, and then into a chaotic solution. Okay, so these are some complex periodic modes which we get from our model. So this is our 3-3. Again, we can compare the takeoff and landing phases, which are not bad. We basically get a quantitative agreement for the simpler periodic modes. When things start getting chaotic, we get qualitative agreement, right? But still satisfactory. And so now if we look at one of our chaotic modes, we can plot again the velocity versus position, and we get this basically an attractor, and we look at the power spectrum, and it's full. and the Lyapunov exponent is positive, right? So that what that says is if we start somewhere in here, we have two points in this phase space which are initially close, they will diverge exponentially, and that's the hallmark of chaos. Okay, and so the Lyapunov exponent I've changed. We had V versus phi. Now for some reason we've gone into polar coordinates, but in any case, this is again the place where it gets energy. This is the part where it loses energy, but you can see that it's all over it's basically filling the map. So each one, so this thing's bouncing all over the place. Okay, and so then one can do other things, mathematical things, because we have such a complete description. Oh yeah, so we get a little revision. We can do a little correction for bouncing period, yada yada. But that's not so exciting. But this is kind of nice. So here's a bifurcation diagram. So this is the forcing acceleration. This is the impact speed. And so you see below a certain threshold, you can't get bouncing. And then you see bouncing, the system supporting bouncing solutions beyond this critical value. The first one being 2, 1, and then 1, 1. And then if you follow these branches as you increase the forcing acceleration, so basically each of these lines has some basin of attraction, right? So if you start here in phase space, you'll basically fall onto this curve. Okay? But so if you follow this one, it'll come along here, and then it branches. So that's a period doubling event. So it's going from a 2, 1 to a 4, 2. Is that right? Well, I clearly updated. Yeah, so it should go from 2, 1 to 4, 2, and then you get subsequent period doubling. So this is a period doubling event, and then it period doubles again, and so on and so on. So if you zoom in, and then beyond a certain point, you get basically almost all the solutions are chaotic, but you have these little windows of periodicity, which is something which is sort of classic in dynamical systems as well. So if we look at these period doubling transitions, so again, so we zoom in. So if we zoom in, this is on the 2, 1 branch here. If we zoom in, 2, 1 goes to 4, 2, and then 8, 4, and you basically, then if you zoom in here, you get this, right? So you really see this nice, and you can look at the power spectrum and see the evolution. So you can see that they are indeed period doubling transitions. And so this is so there's something very nice. Have you guys done dynamical systems?
I've seen a little bit in ordinary differential equations.
So you've seen Feigenbaum numbers? So there's a class of maps, these 1D or area-preserving 2D maps where you get the emergence of this Feigenbaum number. So this is basically looking at the transitions. So these are the thresholds of transition. Okay. So this is gamma I plus 1 minus gamma I. So let's say that one minus that one. So it's so this is the ratio of two lengths. So it's basically this to this, right? So it turns out that if you evaluate this in the limit that you go towards this sort of coalescence of the onset of chaos, this converges to a number, which is this, which is the Feigenbaum constant 4.6692, which is quite remarkable. And so we looked at these, how our things changed, and they kind of look like they might be going there, but I think they maybe aren't. But in any case, it's a good thing to look for. And it's great if you can actually find these things in the lab, right? But so I knew about these Feigenbaum numbers when I was younger, and I was hoping to see them in the lab, but I think it is for a restrictive class of problems, and I don't think they would. I think it has something to do with the map being area preserving, whatever that means. But the other thing is, so in these, when you get maps like this, the ratio of that to that is given by the golden mean. Ooh, isn't that cool?
The ratio of what?
So that to that. So you see this is asymmetric. So there's a class of maps for which that ratio to that ratio is always given by the golden mean. So we were hoping it would have been too good to be true if we got the Feigenbaum numbers and the golden mean coming out of the system. But I was pretty happy with the way it turned out. But these are sorts of things you look at. We looked for.
But you don't approach the golden mean either, right? That's what you're saying.
Yeah, this one. Yeah, but it kind of looks like it. Yeah. But it's amazing the way this number comes out, the golden mean, right? What is it? 1 over 1 plus 1 over 1 plus 1 over... Right?
This equation that you insert in the... Because you're talking about area preserving and things like that. Usually dissipation destroys the area preserving transformation, right? So,
What's that?
I mean that when you have dissipation,
Yeah.
you lose all these area preserving and stuff like that properties, right?
Yeah. Yeah.
Have you looked at the idealized system? Does it change much?
No, not... Yeah, we haven't done. We sort of ran out of... The student was only visiting me for a few months, so we stopped. But in any case, it's sort of a nice... I think it's a nice system in that we get really a nearly exact description of the dynamics from a second order ODE. And we get... we can describe these simple periodic modes quantitatively. We can really describe what we see in the lab pretty much exactly. And then we get qualitative agreement with the more complex periodic and chaotic modes. And this is it's a nice example of a period doubling transition to chaos. And this is certainly one of the cheapest chaotic fluid systems yet explored. So the first examples where they looked at the onset of chaos, and these were really classic experiments. So Liebscher did them, and Golub and Swinney. They were basically looking at convection. So this is something we looked at earlier in the course. You heat a fluid from below, and you get the onset of motion, and then you get onset of periodic motion, then you get a period doubling cascade to chaos. And these are very high-tech, difficult experiments. There's also the dripping faucet is something which also gives periodic behavior. Okay, and so that is it's comparable in terms of level of difficulty experimentally, but it's actually much harder to treat theoretically. So if you integrate over ease of experiment and ease of theory, I think this is the simplest fluid chaotic oscillator. So they have looked at solid chaotic oscillators. So a very simple one is just a bouncing rubber ball on a plate, and there you get onset of chaos and so forth. And that's also relatively easily characterized. But if you guys, so that's the end of the lecture. We can stop there, but I'm just gonna show you guys one other thing. So have you guys seen Fibonacci spirals in plants?